Hello everyone, welcome to the lecture series of the pattern classification. I am Kundan Kumar, and if you would like to have this lecture slides, then you can refer to my GitHub page at this link. So, in this lecture I would be covering these following topics like dimensionality problem, or we can say that the curse of dimensionality. Then we will cover the dimensionality and feature reduction using the two different approaches like principal component analysis and linear discriminant analysis. Under linear discriminant analysis I would be covering Fisher linear discriminant analysis and multiple discriminant analysis, and at the end I will touch the few things about the feature selection. What is dimensionality problem? In practical multi-category applications, it is not unusual to encounter problems involving tens or hundreds of features, even more than that. Let us consider one example of the MNIST dataset. So, MNIST dataset is basically for digit classification, where each binary image having the resolution of 28 cross 28 pixels. So, this image if we flatten it, then you will have the feature vector of dimensionality 1 cross 784. So, that means if we consider each individual pixel as a feature, then we will have the feature vector of dimension 1 cross 784. So, just you think that the dimensionality of the feature vector is not limited in case of multi-category application in practical applications. So, our intuition says that each feature is useful for at least some of the discrimination. That means adding features is basically the good idea, that says our intuition, but it is not always true. In general, if the performance obtained with the given set of feature is inadequate, that means whatever the features are given and that is inadequate, that means that is not sufficient to give the desired accuracy, then it is very natural that we need to add some extra features. So, let us take one example of the XOR problem. So, what is basically the XOR problem? So, if x1 and x2 is the input feature, so we can say that these two feature vectors are input like 0 0 0 1 1 0 1 1. Then the output class, you can say that output class. So, output class is basically this will be 0, output will be 1, output will be 1, and this will be 0. So, we can say that this is the class 1 and this is class 2 and class 1. So, if we draw it in the two dimensional space, then let us draw a circle for class 1 and then cross for class 2. So, you can draw the features something like this in the two dimensional feature space. So, here you can observe that a single straight line cannot distinguish between the two classes. So, that means can we make it linearly separable? This feature is basically not linearly separable, that means a single line cannot distinguish these features. So, can we make it linearly separable by adding some extra feature, because these two features are not sufficient to make it linearly separable. So, let us one extra features, and that we are considering that x1 x2, these two features are already available and we are adding one extra features x1 and x2. So, now what will be our table? So, x1 x2 0, it will be 0 1, then AND operator, then it will be 0 1 0, then it will be 0 1 1, then it will be AND. So, let us plot this. Here we do not want to classify, just plot it and we will check it whether it is linearly separable or not. So, plot a 3-dimensional space, 3-dimensional feature space. So, suppose this is the x1, this is x2 and this is x3, that we are considering that x1 into x2. So, here we will make a unit cube, we can make it okay. Now, draw this feature vector. So, this is the basically the circle that we are drawing for. So, this was for the class information was given, this was basically which class, this was omega 1, this was omega 2 and this was omega 2 and this was omega 1. Okay. So, 0 0 0, then we have 0 1 0. So, this is the point 0 1 0 and this is the cross, then we have 1 0 0. So, this is the cross omega 2 and then 1 1 0. So, this is 1 and 1 1 1. So, basically this circle. Okay. So, now here you can observe that a plane which will pass through something like this, then we can say that it become the linearly separable. That means, this linear plane can separate these features in two different classes. So, even though increasing the number of features increases the complexity of the classifier, it may be acceptable for an improved performance. So, we can add extra features even if the complexity increases, but sometimes we will have the trade off between these two. So, let us take this figure. So, here you can observe that if we consider the only one feature, then we have the distribution of the two class and we have some error, we are encountering some error here. But what if we add one more features, then we will have the 2-dimensional distribution, but still we will have the overlap region, that is the basically the error terms. Then then we can add one more features, then we can see that the distribution of the two different class are basically totally separable. That means, a linear plane can separate these two class. So, adding an extra feature can make it linearly separable. So, he can note down that there is a non-zero Bayes error in one dimension x1 space or the 2-dimensional x2 x1 x2 space. However, the Bayes error vanishes when we add extra feature, that is x3, and we obtain non-overlapping densities. So, unfortunately, it has frequently been observed in practice that beyond a certain point, adding a new features leads to worst rather than the better performance. That means, it is not necessary that every time we will get the better performance. Sometimes by adding feature we can get the worst performance. So, basically that is called the curse of dimensionality. We cannot go beyond that means, we can add features, we are going adding features and we will improve the accuracy. It is not like that. So, there are the two issues that we must be careful about it. So, that is basically how is the classification accuracy is affected by the dimensionality, and how is the complexity of the classifier affected by the dimensionality. That means, the classification accuracy and the complexity of the classifier, that is the basically the trade off that we need to take care. So, these two issues we need to take care, that is the basically the balance we need to make. The error will be introduced in the model. So, how we can make ensure that. So, the wrong assumption in the model selection, that means to solve any problem whatever the model we will select, then it depends on that which model we are selecting. Based on that also our that is the one of the reason for increase in error. Also, when you will have the high dimensional observation, that means high dimensional data you will have, but the you will have the very less number of training samples. So, in that case also we will face the more number of the errors. So, what is the solution of that? Basically the solution of that is the potential solution, that is basically reduce the dimensionality. So, we will have the high dimensional space, then we will reduce the dimensionality and simplifying the estimation. Then whatever the estimation, if we are estimating the density of any of the feature vectors of a particular class, then we will try to simplify it. So, these are the basically the potential solution. So, dimensionality can be reduced by redesigning the features. So, whatever the features we will have, whatever the dimensionality of the features, we will try to reduce it by redesigning or from one dimension one feature dimensional space to another feature dimensional space, or by selecting an appropriate subset among the existing features. Or we can do that, what we can do that, we will select a few features which are very good among the existing features, and also we can combine the existing features. That example that already I have shown you, that I have combined the feature x1 and x2, and that make our model to linearly classify the feature vectors. So, estimation error can be simplified, and the estimation of error can be simplified by assuming equal covariance. So, in some cases we will assume that the covariance of the different classes are same, that we can assume, and maybe in case of the Gaussian distribution case we will consider the regularization. Basically, regularization is the technique used for tuning the function by adding an additional penalty term in the error function. So, in that way also we can estimate estimation of error can be simplified. Then we can consider the prior information and the base estimate to estimate the dimension the distribution of the feature vectors, and then we can use some heuristic such as conditional independence, that the two classes are conditional independent, something like that. So, in that way we can reduce the estimation of error that can be simplified. So, let us see this plot. Here the black dots are basically generated using this function, where this function is basically the quadratic function, and here the noise is added, that is the basically the Gaussian noise with the 0 mean and sigma square variance. So, but suppose we want to fit this the model using the 10th degree polynomial, then you will see that this curve is passing through all the points, but we have generated all these points using this quadratic function. So, that means it is not necessary that we will consider a very high degree polynomial to fit this, where we have generated this data, that means this data following this quadratic function with what, but with some noise. So, so we have to give some trade off between the accuracy and the complexity. So, here if we consider the 10 degree polynomial, then the model will be very complex and sometimes it will be overfitted. So, definitely we will have some regularization, or we will reduce the dimensionality, that means a degree of the polynomial, that means second order function is sufficient to estimate this the curve fitting problem. So, all of the commonly used classifier can suffer from the curse of dimensionality. So, the curse of dimensionality, every classifier basically suffers from the curse of dimensionality, that need to be taken care. While an exact relationship between the probability of error and the number of training samples, number of features and the number of parameters is very difficult to establish. Some guidelines have been suggested. It is generally accepted that using at least 10 times as many training samples per class as the number of features is a good practice. So, this is the some a general guideline that is already given. So, we can consider that the number of samples and the dimensionality ratio should be greater than